Dr. M.A. Bhagaveni, Professor, Department of Electronics and Communication Engineering, College of Engineering Gindi, Anna University, Chennai. Dr. M.A. Bhagaveni graduated from Government College of Technology, Coimbatore, has completed her Masters and PhD at College of Engineering Gindi, Anna University. Her field of interest includes cognitive radio, ad hoc networks, wireless sensor networks, and wireless communication. She has completed 2 projects, one for CVRDE and the other for DST. She is the recipient of Young Scientist Award from DST. She has got 2 Best Research Paper awards in international conferences. She has published more than 70 research papers in reputable journals and conferences. She is author of 2 books. The one is Analog and Digital Communication and the other is Cognitive Radio, an Enabler of Internet of Things.
Welcome to the UGC lecture series for BSc Honours. This session we are going to see about frequency demodulation experiment. The aim of the experiment: to perform a frequency demodulation using IC 565 PLL and verify that the demodulated signal is found equal to the modulating signal. The apparatus required to perform these experiments are the audio frequency generator, also called as frequency generator, the PLL IC number 565, resistors, capacitors, CROs, breadboards, connecting wires and regulated power supply. The process or the theory for FM demodulation. Here the process of FM demodulation is to extract the original modulating voltage from the frequency modulated voltage. PLL is used to convert FM modulated signal into original modulating signal. The phase detector produces phase error signals between the 2 points. This phase error signal is passed to the low pass filter, which will produce an equivalent DC voltage with respect to the phase error. This DC voltage, once it is been given to the voltage control oscillator, the VCO will produce a frequency based on the given DC voltage. From this DC voltage, from this frequency, you can just track out, this will be once again fed as input to the phase error circuit. The phase error circuit and the input signal will be just compared. If the phase of the input as well as the phase of the signal that is produced by the VCO are not correct, this will provide an error signal. This error signal will be converted to a DC voltage. The DC voltage will produce another frequency. So, like this it continues as a loop, that is why this is called as a phase lock loop. Here we need to see about 2 different things, that is called as lock range of the PLL as well as capture range of the PLL. There will be a oscillating frequency F oscillation. From this oscillating frequency, this is the oscillating frequency of the VCO. You can provide any input signal for the PLL to capture it. So, if the input signal is outside the lock range, if you are providing a frequency outside this value, the PLL will never able to track it, or you won't get a exact replica of the modulating signal. So, you should see that whatever signal you are giving as input should fall within the lock range of the PLL. So, within the lock range, in the sense the error produced is trying to get corrected. The error is repeatedly trying to get corrected, and finally, whenever the frequency of the input signal as well as the frequency of the VCO is matched, then we call it as a capture range. The PLL has captured the signal. So, even if there is one small delta changes, still it can capture it, in the sense that VCO will able to adjust its frequency and produce a sinusoidal signal which is same as the input signal. So, the PLL circuits will try to track the FM modulated signal if the signals are within the lock range and exactly captured if they are within the capture range. So, with this knowledge we can just see what are the pin configurations for the IC 565. It is a 14 pin IC. Pin number 1 you need to connect a negative voltage minus V. Pin number 10 we will be providing a positive voltage. It is a bipolar input signal. Then pin number 2 and 3 will be providing input signals. Pin number 4 we can see the VCO outputs. Pin number 5 it is the input to the phase detector from the VCO. Pin number 6 is the reference output. Pin number 7 is the demodulation output. Pin number 8 you will be connecting an external resistor to set up the free running frequency of the VCO. Pin number 9 will be connecting an external capacitor to set up the free running frequency of the VCO. Rest of the pins after 10 like 11, 12, 13 and 14 are for future use. So, it has no connection with respect to this experiment. So, this LM 565 pin configurations, a detailed descriptions of the pin configurations is, it is a 14 pin IC operated from a dual power supply, plus volt is given to pin number 10, minus volts is given to pin number 1. Pin number 2 and 3 are the pins which will take up the input signals for phase detections. So, pin number 4 is VCO output is available, which should be connected as one of the input signal to the phase detector. Pin number 4 and 5 are shorted externally, so that the VCO output is applied to the phase detector. In certain applications, we will be need to break the PLL loop. In some circuits, both the pins are connected. Pin number 6 will be providing a reference DC voltage. Pin number 7 demodulated output is viewed. If the input signal between pin number 2 and 3 is an FM signal, then at pin number 7 what we are going to get will be the FM demodulated output. Pin number 8 and pin number 9 will be connecting an external resistor R1 and C1 to determine the free running frequency of the voltage controlled oscillator. The internal resistance R2 and the external capacitor C2, they forms the low pass filter circuit in order that the higher frequencies are removed. So, the value of the internal resistance is R2 is fixed to 3.6 kilo ohms. We can plan up what should be the value of C2 in order that the low pass filter cutoff frequency will be determined. This is the demodulation circuit diagram for LM565. So, pin number 1 negative minus 6 volts is provided, pin number 7 positive 6 volts is provided, pin number 10 positive 6 volts is provided. Pin number 7 will give you the demodulated output. Pin number 6 you will get a reference output. Pin number 4 and 5 are shorted in order that we have already seen it has been shorted to take up the output of the VCO to the phase detector. So, at pin number 8 we are connecting a resistor R1, pin number 9 we are connecting a capacitor C1. This value of resistor R1 and C1 will determine the free running frequency of the VCO which is available inside the PLL. The capacitor, this 1000 picofarad capacitor will determine the low pass filter cutoff frequency, the low pass filter cutoff frequency. There are two inputs, either 2 or 3 we can provide the input signal. In this case we are providing the input signal at pin number 2. The input signal will be FM modulated signal. The input signal will be FM modulated signal which this PLL should track on. The design process, let R1 to be equal to 4 kilo ohms, the capacitor value selected to be equal to 1000 picofarads, C1 is 0.001 microfarads, C2 0.01 microfarads. The operating voltages be plus 6 volts and minus 6 volts. You can set up any value between plus 6 volts to minus 6 volts or plus or minus 12 volts. So, for calculation purpose we have taken up V to be equal to 12 volts. You can also have V to be equal to 6 volts and proceed and do the same set of calculations to get what will be the values of the free running frequencies of the PLL or the VCO. To get the free running frequency of the VCO, it is calculated as 0.3 divided by R1 into C1, 0.3 by R1 into C1. So, 0.3 by R1 value is 4K, C1 value is 0.001 microfarads. Once you substitute, you will get a value of 7.5 kilohertz. This is the center frequency of the PLL. Then you can find what is the lock range of the PLL and the capture range of the PLL. To obtain the lock range, it says it is nothing but the frequency range over which the loop remains locked, the range of frequencies which the PLL can track. So, that is why it is called as lock range. So, FL is obtained as 8 times F naught divided by V. FL is obtained as 8 times F naught divided by V. So, 8 times 7.5 kilohertz divided by 12 volts will give you 5 kilohertz. This is the lock range. So, in order that to capture the changes or to get a fruitful demodulated signal, the del f should be within 5 kilohertz. The del f max and f min signal that is provided by the input modulated signal should be within 5 kilohertz, then only the PLL can track. The capture range of the PLL FC is nothing but 1 by 2 pi root of 2 pi FL divided by R2 into C2. So, when you substitute the values for lock range value as 5 kilohertz, R2 is the internal resistor that is already set, C2 is 0.01 microfarads. Once you give this set of values, we will get the capture range to be equal to 4.988 kilohertz, 4.988 kilohertz. Just see what is the R2 value that is already set, which will determine the R2 is external capacitor, it is set to a value of 3.6 kilo ohms. So, in the design value we need to substitute R2 to be equal to 3.6 K and C2 to be equal to 0.01 microfarads. So, you will get a capture range for the PLL which is 4.988 kilohertz with respect to this set of readings. So, that is why while writing your apparatus required, I have not given any of the values for resistor, capacitor, etc. So, these values are determined only at the design level. So, if we are just selecting V to be equal to 6 volts, we get a different value, right. All these things we get different value. So, at the apparatus required level, we have generally discussed that we need some resistors, we need some capacitors. The exact values of resistor capacitors will be designed using design equations. So, once you fix up the center frequency of the PLL, the lock range of the PLL and the capture range PLL, then you go ahead with doing the experiment. The procedure to do this experiment is: step 1, the circuit is connected as given in the circuit diagram. Step 2, the FM input signal is applied to pin number 2, which is the input to the phase detector internally. The pin number 4 and 5 are shorted externally to complete the loop. Initially, the loop is locked onto the carrier frequency. As carrier frequency changes, we get a demodulated output at pin number 7. The resistor R1 and C1 connected externally determine the oscillator frequency F naught. How they determine, we have already seen in the design equation, and the external capacitor of 1000 picofarads is connected for the stability of the internal circuit. So, these are the procedures. Once we have given you the input signal, a FM modulated input signal, and if the del f of the FM modulated signal is within the lock range of the PLL, at pin number 7 we will see the demodulated output. The signals that are to be noted down are: what is your input signal? The input signal is FM modulated input signal. So, this is a sine wave where the frequency reduces and then raises. Amplitude of the signal is becoming less and then increasing over this part of the waveform. So, this is a modulated input signal. You can also give this is another modulated input signal. The green color says the FM modulated the carrier signal, This is your carrier signal, and red signal is nothing but the message signal. When the carrier signal and the message signal are FM modulated, you will get this, you will be getting this blue colored signal, which is FM modulated signal. As the amplitude reduces, the carrier frequency reduces. As the amplitude increases, the carrier frequency increases. So, you can see the blue colored signal is a FM modulated signal. This signal will be given as input to pin number 2 of the 565 PLL. So, by tracking the changes in the frequency, we get a demodulated output, which is nothing but this red color waveform itself. Similarly, if you are going to provide an input of FM modulated signal whose message signal is like this, we get a demodulated output as the same. I have just shown you 3 types of signals. This is only FM modulation signal, this is a carrier with FM signal, then FM modulated. With FM demodulation, you will get back your red color signal here, whatever as demodulated signal. Otherwise, if this is your input signal, you will get back your this signal as your demodulated output. So, these are the waveforms you are going to note down when you do FM demodulation, and cross check whether the output whatever you have got is same as the message signal whatever you have provided. So, that completes your FM demodulation experiment. The results for this experiment is the FM demodulator circuit is implemented using IC 565 PLL, and the demodulated message signal is found. In summary, we have just built up a FM demodulator circuit using IC 565. The IC 565 is a phase lock loop IC, which will have a phase detector. The phase detector compares 2 input signals. One will be your FM modulated signal, the other will be the output of the VCO, the internal VCO that it has. Whenever the phase mismatch is between the externally connected FM modulated signal and the internally generated VCO, an error signal will be produced. This error signal will be equivalently converted to a DC voltage. The DC voltage will be provided as input to the VCO. Now, the VCO will generate a sine wave signal with respect to the voltage that is applied to it. So, like this will run in continuous loops to track the changes in our input signal. So, thus at pin number 7 we can see the demodulated output, FM demodulated output, and the waveforms will be noted down. This completes this session. Thank you.